In this lecture, we'll cover some techniques for designing experiments when there are multiple treatment factors. So let's start off with a pretty simple example, just to demonstrate that the idea of a block design can still be relevant. Suppose we have two treatment variables. Each one has 3 levels. The first treatment will denote the levels as 1A, 1B, 1C, and the second treatment will denote the levels 2A, 2B, 2C. And if we have 18 units, we can divide the units into 2 blocks, each one having 9 units. The reason for doing this is because in each block, we can allocate each treatment combination exactly once. So since there are 3 levels of each of these 2 treatments, there are 3 times 3 equals 9 possible combinations. So when you have more than one treatment factor, you can still do something like a complete block design. So this kind of thing will work when the number of units is a multiple of the total number of treatment combinations. But as you can imagine, if you had, say, 6 different treatment variables and 4 different levels of each of those, the number of possible combination would be 4 to the 6th power, which is a very large number. And so if you have a lot of treatment variables and there's lots of possible levels, then you have to kind of do something different unless you have a very large number of units. So the example I give down here is if you had 5 treatments, each with 3 levels, there's 3 to 5 possible combinations. And so for many situations, designed experiments, you can't run all those combinations even once. So in these situations, when there's many treatment factors, you either need a lot of units. In this case, you need 243 possible units to do every combination. Or what it usually happens in practice is that we do a smaller experiment that we call a screening experiment to determine which of the treatments are really the most important or have the greatest influence on the response. So one of the most commonly used techniques for these types of screening experiments is called a factorial design. So in a factorial design, the notation we'll use is we have k treatment factors. So in the example above here, there were k equals 2 factors. For each of these treatment factors, we assign only 2 levels. So oftentimes the treatment factor will be a variable that's continuous. In those cases, we'll pick just a low setting and a high setting to be the 2 levels for that factor. To do the 2 to the k factorial design, which is also called the 2 to the k full factorial design, you need 2 to the k units. So if you had 4 different variables, k equals 4, you would need 2 to the 4 equals 16 units. And the design is very simple. You just do one experimental run at each of the possible 2 to the k combinations. So let's start with just a really simple example, and we'll build up to higher numbers of treatment factors. So here k equals 2 treatment factors. There are 4 possible combinations. If we label the levels of the 2 treatment factors A and B, the 4 combinations are denoted like this. So treatment factor 1 at A, treatment factor 2 at A, treatment factor 1 at A, treatment factor 2 at B, factor 1 at B, factor 2 at A, or factor 1 at B, factor 2 at B. So these are the only 4 possible combinations. The 2 to the k factorial design simply says that we do an experimental run at each of these combinations. So we need 4 units. We do 4 We collect 4 responses, 1 from each combination of the treatment factors. In the reading material, we lay out the designs in tables where each row of the table corresponds to 1 run of the experiment. In the notes here, I'm just for some variety for how we present these things, I'm going to show you these diagrams for how to look at the experiments. So in the diagram, the way this works is the vertical axis is the first treatment factor. So the vertical axis can be either level A or level B, and the horizontal axis is the second factor. So the left side is level A and the right side is level B. So the way we draw this design is we put a circle at each of the possible combinations of factor 1A or B and factor 2A or B, and we fill in the circle in black if the experiment gets run at that particular combination. So what this means here is we run one experimental run with both at A, one with factor 1 at B, factor 2 at A, one with factor 1 at A, factor 2 at B, and one with both at level B. So each of these corners of this little diagram corresponds to one of these treatment combinations. Let's do the example with K equals 3. So if there are 3 treatment factors, 2 levels for each factor, that means there are 2 times 2 times 2 equals 8 possible combinations of the low and the high setting for each of these. So this just enumerates all of the possible combinations. If you count them up, there are 8. If we want to diagram the factorial design, we can diagram it with this 3-dimensional figure. So here I've labeled this axis as factor 1, the vertical axis as factor 2, and the depth axis as factor 3. So each of these circles here in the diagram corresponds to a particular setting for each of these factors. So let's circle out this one here. So this means we've set factor 1 to A, we've set factor 2 to B, and factor 3 to B. So this would be, this particular setting will correspond to this particular run of the experiment. So very simple. Again, we just do the 2 to the 3 factorial design just means we do a run at every possible combination of each of these 3 factors. Now we start to get into trouble diagramming the 2 to the 4 design because we don't have a 4-dimensional space, but we can kind of fake it here. So what this means is all of these runs on the left correspond to factor 4 at its low setting, and all of the runs on the right correspond to factor 4 at its high setting, and then each of the dimensions in each of these corresponds to the same dimensions as in the 2 to the 3 design. So here there are 16 possible combinations. Each possible combination corresponds to one of the circles on this diagram. And then if there are 5, it's 2 to the 5 equals 32, and so on and so forth. Now, as you can imagine, if you had, for example, 10 factors you wanted to study, you would need 2 to the 10 units, and which is 1024, which is probably too large for most settings. So the concept of a fractional factorial design is very useful here. So what all a fractional factorial design means is you take the 2 to the k design, which we also call the full factorial design, and we do a fraction of the runs of the full factorial design. Now, there's a specific reason for why we pick a specific fraction. So what I'm going to describe first is the 2 to the k minus 1 design. What that means is it's the 1/2 fraction of the 2 to the k design. So we take the 2 to the k design and we do half of the runs. But we pick the specific half to satisfy a certain criterion. And the criterion is this. If you were to delete one of the factors, then you will get a full factorial design in the remaining k-1 factors. So let's see how this works in some specific examples. So the 2 to the k-1 design when k equals 2 means we have two factors, factor 1 and factor 2 in the vertical. Instead of doing 4 runs, we do half of those. We do 2 runs. So what this diagram is saying is that instead of doing all 4 combinations, we do a run at AA and BB. So this is an example of a 1/2 fraction design. But it satisfies the constraint that we imposed, meaning that if we deleted one of these factors, we would get all possible combinations of the other factor. So let's see how this works. If we imagine, so let's see, horizontal is factor 1, vertical is factor 2. If we were to delete factor 2, that means we're collapsing this design along the factor 2. And so this one will drop to here, and we have both settings of factor 1. Another way of looking at this, if we just look at this design, we have one run at the A level of factor 1, and we have one run at the B level of factor 1. The same is true for factor 2. We have one run at the A level and one at the B level. Actually, these should be switched. This should say B here, and this should say A here. There's one other valid 2 to the k-1 design that satisfies our criterion. It's just you take this design and flip it. So you do the runs that you didn't do here, which ends up being this design. So we have one run at level A of factor 1, one run at level B of factor 1. We also have one run at level A of factor 2 and one run at level B of factor 2. Okay, so the higher ones are obviously going to be more complicated, but what's going to be true is that for every 2 to the k-1 design, there are 2 possibilities. So just like here, there are 2 valid 2 to the 2-1 designs. There are going to be 2 valid 2 to the 3-1 designs. So these are kind of fun to think about. So imagine taking this. So this is a valid 2 to the 3-1 design. Imagine taking your hand and smashing the top of this design down, which means we move this point to here and this point to here. We're left with all possible combinations of these 2 factors on the bottom. And then we can think about smashing it in any direction. So if we smash in the horizontal, we'll take this one and move it here, this one and move it here, and then we'd have all combinations here. We could also smash in the depth direction, which means we would move this one here and this one here, and we'd have all possible combinations of these 2 factors. The other valid 2 to the 3-1 design is just the opposite of this design. So wherever we didn't do a run in this design, we do one in this design. And then you can imagine doing the same thing. Smash it in any direction, and you get a full 2 to the 2 design and the 2 remaining factors. The reason for this and why this is useful in a screening experiment is you may have 3 factors that you think may influence the response, but you think that probably they're not all going to be influential. You just don't know which one. So that's why you're running the experiment in these 3 variables. If you run the experiment and you find that one of the variables, say factor 1, is not important, then you can rerun the analysis without factor 1 and have a full factorial design to work with in factors 2 and 3. Just for fun, let's do the 2 to the 4 minus 1 design. These are the two valid designs. So you can imagine if you were to ignore factor 4, then you would take this point, put it here, this one here, this one here, and this one here, and you would get a full 2 to the 3 design in the first three factors. If you were to take any other one, you would get the same thing. So I'll leave that for you to try on your own. But these are the only two valid 2 to the 4 minus 1 designs. All right, so the idea here is we have several factors we want to investigate. In the factorial design, we pick 2 different levels for each factor and either run all possible combinations, or if we don't have enough units, we do a 1/2 fraction, or there also are 1/4 fractions, so on and so forth. And that's described in the reading. The way we usually analyze the data for these screening experiments is we'll fit an additive model with a term for each factor. Try to figure out which are the most important factors, and then if there are any that are unimportant, we delete them and then fit a more complicated interaction model in the remaining factors. So this is just a short little exercise about model degrees of freedom for these models. Just to review, in the additive model, the number of degrees of freedom for the k equals 2 model will be 3. The reason for that is you can imagine a 2 by 2 table. In order to specify all the expected values for this 2 by 2 table, you would need to know everything in the first row and the first column, and then the fourth entry is redundant given the constraints of the additive model. So there's 3 model degrees of freedom. The 2 to the 2 design has 4 runs, and therefore we have 4 minus 3 equals 1 residual degrees of freedom. So the 2 to the 2 design allows us to estimate the additive model in 2 variables, and we can get an estimate of the variance, but it's based only on 1 residual degrees of freedom. So it's not going to be a very reliable estimate of the variance. In the k equals 3, so 3 factors, we have 8 runs in the 2 to the 3 design, and the model degrees of freedom is 4. And so therefore we have 4 residual degrees of freedom, so we can get a little bit better estimate of the residual variance. In general, in the 2 to the k design, the model degrees of freedom is going to be 1 plus k, and the residual degrees of freedom is 2 to the k minus 1. So as long as, so in every case we can estimate the additive model because we have more data points than model degrees of freedom. For the interaction model, it's not quite so easy. So let's just review what the interaction model looks like for 2 variables. Essentially the way, before we look at the equations, the way we think about this is if there's 2 factors and there are 2 levels for each, we can describe the expected value for this model with a 2 by 2 table. So there are 4 cells in the table, and unlike the additive model, in the interaction model, there are no constraints on how the values of the expected values in each of these 4 cells have to be related. So therefore, the model degrees of freedom is 4. In the 2 to the 2 design, we have 4 observations, and so we have no residual degrees of freedom. So we can generate estimates of the means for these 4 cells, but we can't get any uncertainties about those estimates or any estimates of the residual variance. If there's 3 factors, the way to think about this is we have 8 possible combinations of these three factors. And in the full interaction model, there's no constraints on how those expected values have to be related. And so the model degrees of freedom is 8. So what ends up happening is if you want to fit a full interaction model using a 2 to the k design, you have exactly the same number of observations as you have model degrees of freedom. So you can get some information about what these expected values are, but you can't get any uncertainty about them because you have nothing left to estimate the residual variance. So usually the way, and things are even worse if you have a fractional factorial design. You simply can't fit a full interaction model, so a 2 to the 3 model, if you use a 2 to the 2 minus 1 design, 2 to the 3 minus 1 design, because you would have 4 observations in that design, and the full interaction model has 8 model degrees of freedom. So the way the data usually get analyzed here is we run a full factorial design or a fractional factorial design. We fit an additive model, so we'll usually have enough degrees of freedom to estimate all the parameters in the additive model. We try to figure out which variables are unimportant, and then we delete them or screen them out, and then rerun the fit for the remaining variables. Okay, so I basically just said in words what's left over in the notes here. So that's the basic idea. There's this full factorial, fractional factorial, they have complicated names, but it's really not too complicated. The full factorial just means you do all the possible combinations and do an experiment with 2 to the k runs. And fractional factorial is you do a fraction of them. So the half fraction, you do half of them. There is such a thing as a quarter fraction where you do a quarter of them, but you do have to be careful about how you pick which half to run, and there's a logic behind that. So the logic is that in the half fraction, if you deleted one of the variables, you're left with a full factorial design in the remaining variables.